series present. We are very happy to welcome Dr. Zhang Bian from the University of Florida. Dr. Bian currently serves as professor and division chief of biomedical informatics, as well as the chief data scientist and chief research information officer for the UF Health System. He earned an engineering degree in China before coming to the University of Arkansas, where he earned master's and PhD degrees in computer science and integrated computing, respectively. After serving on the faculty at the University of Arkansas, he joined the University of Florida, where he's leading a number of efforts focused on all things artificial intelligence and data science. I've had the pleasure of working with him in some of our CoreNet activities, and very much looking forward to today's presentation. Dr. Bian, thank you very much. I'll turn it over to you.
Thanks, Tom, for the nice introduction. Thanks for the opportunity and the invitation. I tend to do bad in terms of timing of the talk. I have about 40 slides, and there are some slides I can skip. I would like this to be more interactive discussion. So if you want to interrupt me for a question, please do. I like to deliver overall message, one or two that I think it's important for the community to know. At the end, if I can deliver that message, that's great, even if I cannot finish all the slides. It sounded like a lot of titles, and it is a lot of titles, but essentially they are pretty much doing the same thing in terms of real-world data infrastructure and then how to use this infrastructure to advance clinical, translational, and basic science. I have the kind of equivalent title like Tom as the CIO, where I oversee the data warehouse, and then for UF Health, and then for One Florida, which is the One Florida Clinical Research Network, another PecoNet sites like Insight. I serve as the chief data scientist. This is probably going to be the least amount of AI you're going to hear from me. As you can see from the title, it's more about data, problems, opportunities, and sort of using AI as a showcase. My training was in computer science, but wasn't really in data science and AI. I actually did data security for years and distributed computing for years. And in my early career, I kind of resisted the AI concept because I thought it's like a voodoo. What does prediction mean? I mean, it's a gas association. But obviously, there's a lot of development in the last 2 decades, and I at least have some beliefs in AI now. So let's get started. This is just a disclosure of the different funding sources. I'm not a methodologist, but I'm not a disease-focused content person either. A lot of my research are translational and connecting between methods and the specific disease areas. I'm somewhat disease agnostic, but obviously if you play the NIH game, it has to be somewhat disease specific. This is agenda. I want to kind of quickly talk about what is real-world data and then some of the thoughts on real-world data. I want to introduce One Florida a little bit, kind of advertising nationally as a national real-world data resource. Some of the studies related to real-world data with AI, with some of the focus on NLP, just because it's our recent work. I do want to spend some time talking about the data issues and modeling issues in real-world data and how to generate real-world evidence. The FDA's real-world evidence framework is still evolving, and obviously, from a method and data perspective, we're also evolving. I do want to talk about the difference between conventional models and prediction models and the importance of causal AI. And then 2 or 3 slides talking about what's next beyond just modeling. What is the real world impact? Real world data kind of hot in the last, I don't know, 5, 6 years. It's not a new concept. If you read the official definition from the FDA, it's the data related to patient health status and the delivery of the healthcare routinely collected from a variety of sources. It's somewhat non-specific, but generally we comparing it in contrast to clinical trials, where so the randomized control trials are very rigorous. They have fixed visits. The data quality are high, but the issue will be a lot of time generalizability, small population size, a small sample size, and then the generalizability is a little bit difficult. So real world data and real world evidence was thought to be the complementary data sources and the importance to look at generalizability and population representativeness. Some of the examples of these data sources are EHRs, obviously, but obviously it's not built for research studies. It's built for billing procedures. Everyone probably have heard that. So there are tons of issues within the EHR data. The claims data, the disease registries such as tumor registry and many others. If you look at the official definitions, there's wearables, home devices, but I'm going to primarily talk about the data that's routinely collected from the healthcare delivery. And the other message I want to make is when you look at individual data sources, it's incomplete picture of the patient. It's more powerful when you have these different data sources linked. For example, we have a lot of effort in PCORNet talking about linking the EHR data with claims, with death registries, with other registries, so that we can actually have a more complete picture of the patient's health. And the study will obviously be more rigorous and more robust. This actually came from my quote unquote job talk slide when I pitched the idea of UF Health needs a chief data scientist. This is my personal view. Not everyone's gonna agree to this, but I think data and data infrastructure is the center of AI in translational research. And as a matter of fact, it's center of any research, right? So all the research we do are about collecting, analyzing, interpreting data, translating them into evidence and findings. So it's the central piece. And all my work has been around how to create these robust data infrastructures. If we look at the healthcare systems, we obviously have, especially in academic health systems, you as a data scientist or methodologist, tool developers, we do AI and data science research, trying to figure out models and tools to get insights out of these data sets. And we, in turn, generate applied AI tools, for example, clinical decision support tools. A lot of them now are AI-based, but we haven't really seen a lot of them implemented in the routine care yet. And then the other part is, in addition to real-world data, the research data is also valuable. And so we have a lot of efforts at UF Enterprise talking about and building these research data commons from disease to disease, and then collectively becoming the large data commons. And when you have those linked, it's obviously more powerful. You have both the benefits of real-world data as well as high-quality data from the research cohorts. And AI is not just about developing methods and tools. It's about the real-world impact on improving the clinical and community outcomes. So I kind of have a key interest in transition from just the infrastructure to what's the impact. Are we actually improving patient care or something? Are we improving population health? I like, so a lot of you probably are familiar with of influence from the social ecological models. If you are happy background, looking at individual, interpersonal, community, and societal issues, and then you have different domain of influence and talk about different data. Right? So you have your biological data, behavior data, physical and built environment, and social determinants, which is the social cultural environment, and then the health system. All of them in each cell affect human health at different level. So we can look at individual health with this framework. We can look at family health and community health and population health. And a lot of our work are structured around the NIMHD research framework. I want to switch gear, always talk about the One Florida Clinical Research Consortium. As I said, it's very much the same as the Insight Network. One Florida started with a pilot, actually a CTSA pilot grants back in 2009, even before I joined UF. It was initially just a collaboration between UF Health and University of Miami. We missed PICORE phase 1. We competed for PICORNet phase 2. And we got founded as initially the One Florida Network because it's covering 8 Florida healthcare organizations initially. And then in 2020, we extended to Georgia and Alabama through a collaboration with Emory and the University of Alabama, Birmingham. And recently, PICORNet has done the PICORNet expansion bridge funding, and we use the opportunity to extend one site in Florida, which is the Jackson Memorial Health System, which is actually the largest FQHCs, I think nationally. So it adds a lot of the disparity populations. And then we reach out to University of Arkansas for Medical Sciences, which I spent 10 years there. So call some friends and participated in Florida, and also University of Irvine, California, Irvine. So we currently have about 20 million patient records from 2012. It covers mostly 17 million Florida, 2 million Georgia, 1 million Alabama population. Adding California, Arkansas, and Jackson Health, Jackson Health is probably going to get us to about 24, 25 million at the end of this year. These are just some of the key features. It's very much like Insight. It's a centralized data repository. The majority of the data is the electronic health records. Then we link it to various different data sources. We have complete Florida Medicaid data, and we have some of the selected Medicare data and some of the primary payer. And obviously, private insurance companies are hard to work with, so we have very little private insurance data. And then we link it to different disease registries like the tumor registry from the FCDS, the Florida Cancer Data System. One unique linkage that we've done is what we call the mother-baby link, which is based on the birth certificate. So based on birth certificate, you can establish the mother-baby link, and then you can correspond to the EHR records, and you can follow them longitudinally by virtue of the EHR, so that you can actually study, for example, mother's health status impact on baby's health. So it's a unique advantage, at least for maternal health studies. I talk about data a lot, but it's not just a data network. It's a clinical research network. Our patient can be identified. So if you want to run clinical trials, we have the infrastructure like Insight to go back to the partner sites, identify site investigators who are interested in particular study and recruit patients. And we've run a number of large HP calorie, all kinds of studies prospectively as well. I think most of piconet sites have similar goals. The goal of One Florida is to help identify study population for prospective studies. PCORI has a large focus on comparative effectiveness, so comparing treatment, drugs, devices, using real-world data to generate real-world evidence is a key focus. Conduct clinical trials in real-world means the programmatic trials we want to do. Then there's obviously a piece about translating these evidence into practice. It's a close partnership. All One Florida partners have a say in the executive committee. They actually vote on every single studies. We also have partnerships beyond just health systems. In addition to payer, we have state health system, state agencies, and we have industry partners as well. I think I got a question. I think I got a question about all these records are de-identified. This is a HIPAA limited data set. So in sense, it's not fully de-identified. We do have dates and locations. This is based on HIPAA rule. There's not a special consent because by virtue of your consent in your health system, secondary use of EHR for research is allowed. This is just a different view of the data trust. As you can see, we get these different data sources. We do standard extract, transfer, load process to harmonize them into common data models. We follow both the PCORNet common data model because of the contract, but also the OMAP common data model out of the Odyssey network because it's wide adoptions. And I know there are a lot of debate nationally in informatics on which common data model is the best. In my mind, my opinion is it's not the best. It's all depending on your use cases and depending on the network you are participating in. Probably like Cornell and Insight, we participate in all kinds of studies from different agencies, some of them even international. We support all kinds of data models for this. There's an access portal for investigators. You can query it through self-servicing query tools like IGB2, and then we're standing out Atlas query tool out of the Odyssey network. You can identify your cohorts. You submit a protocol to One Florida Executive Committee, getting partners approval. Then with IB approval, you can actually get line level data. And if it's a prospective recruitment study, obviously there are clinical engagement with individual sites as well. So that's kind of the data infrastructure I want to talk about, and then I want to talk through a few of the studies that we've done, get a showcase what these real-world data can do and some of the problems with it. I always like to start with this study. This study is already very old. It's already we're already in no-cost extension period, but this is one of my first R1s when I was probably still junior faculty, mid-career faculty. So this is about benefits and harm of lung cancer screening. The clinical story is lung cancer screening is fairly well established. The low-dose CT was showing to be very effective from 2012 lung cancer screening study, large trials, and show it's very effective. But even in the original trial, the false positive rate is a concern. It's about 20% as reported in the original trials. And then based on our study, the false positive rate is actually more than 40% in real world data studies. And the problem with that is, I mean, if it's false positive, you still have to go through the invasive diagnostic procedure. Oftentimes is biopsy, right? Then you would take a tissue out, you go through pathology, and then determine whether it's cancer or not. If it's false positive, and the rate is 4 out of 6, 4 out of 10, then all of those patients just gone through unnecessary invasive procedures, and they will develop post-procedure complications. And post-procedure complication rate in the original trial was about 10%, and again, in real-world data, it's much higher. It's almost 17% using warm fluoride data. And then there's tons of downstream consequences. So our proposal initially was to use warm fluoride to, one, generate real-world evidence on the benefits and harm of low-dose CT to help physician and patient make informed decisions. And then the other, and when you get into decision making, our aim 3 is a macro simulation model so that we can help individual patients based on their smoking history, based on their past medication use and other conditions, and kind of tell them if it's false positive, what's the risk of your lung cancer, whether you should go through, based on guideline, the lung cancer screening or not. If it's false positive, what's the downstream consequences is. If you look at the original lung cancer screening guideline, this is already the 2013 old guideline from the US PSTF, which is age, smoking history, or criteria, which basically means you have to smoke 1 pack a day for 30 years, then you're going to be high risk. But this gets into something what we call spillover effect. A lot of people who may have, I mean, I had about 2 or 3 years of smoking history when I was young. I saw these TV ads recommending lung cancer screening for smokers. If I don't understand the science, I'm not inclined to ask my physician to do lung cancer screening. And oftentimes, since it's unfortunately the U.S. healthcare system, if you try to convince the physician, your PCP would eventually order lung cancer screening, and then you're going to go under different unnecessary procedures. So it's only beneficial for high-risk population, not low-risk population. But one of the key factors of determining whether it's high risk and low risk, besides age, is smoking history. Right, 30 pack year is a very hard bar to get to. And we obviously encounter issues when we using electronic health record data. If you're familiar, if you're a practicing physician, you know smoking history is pretty documented and very inconsistently documented in EHR. Pack year information is non-existent. If you look at public records from 2018 and before, more recently, gradually you have those discrete fields in EPIC capturing pack year information. But they do exist in clinical notes, especially if you're talking about lung cancer screening. So in that population, those information does exist. So this is where we realized natural language processing pipeline is very important to actually extract this information that's not in the structured data. And we did this very early on in 2019, and we actually started with a very simple, just a rule-based NLP pipeline to extract pack year and smoke years. And as you can see, the performance is excellent. Even with very simple rules, we can get to a position of 0.96 and F1 of 0.96. But this actually led us to explore NLP quite a bit. almost 80% of the important clinical information are locked in clinical notes. I don't want to belabor the points. A lot of the family histories, over-the-counter drugs, drug adverse events, social, behavioral, environmental determinants, they all exist only in clinical notes. So NLP is the key technology to, one, identify the cohorts, as you can see from the lung cancer screening study, but also to support AI for clinical decision support to at least add in the missing information that's not directly available for AI models. So we had an NLP grant from Picori. It's a collaboration with Dr. Yonghui Wu, who is the true NLP expert, looking at social determinants of health from clinical notes. It's already in the no-cost extension again, but we've developed a set of open source tools which you can actually use now and adopt to extract social determinants. We were able to extract 17 categories, and on the right, you just see some of it here of the social determinants. And then we have a number of studies based on the social determinants information that we can actually extract from real-world data. Another opportunity about NLP came is U.S. aluminum. He donated. The legend where his wife convinced him to donate $50 million to UF. So we established the partnership with NVIDIA. They give us at the time, A100 system. So the NVIDIA GTC conference was just in the last 2 weeks, and they announced the new B200 GPU, and A100 at the time was the state of art. But that gave us 11,000 A100 GPUs, and then you have put a significant investment in this. And for that collaboration, they came to us, what can we do with this GPU? So we want to showcase it. That's back in 2021, and collaboration started in 2020. The GPU cluster is alive early 2021. And that's actually before anything about the GPT-4 and ChatGPT. So we collaborated, developed the largest clinical language model using the BERT architecture in 2021. We use RUF health notes, which is about 82 billion clinical words combined with some of the general domain nodes. The largest model at the time was 9 billion parameters. We trained it, used over 1,000 GPU, and it took us 17 days of runtime on those GPUs. So it's massive models. And someone estimated, not me, that cost us about $600,000 to just train that model, considering the electricity and the infrastructure cost. And then actually before the ChatGPT and GPT-4 came out, NVIDIA had a license with OpenAI on the GPT-3 model. So we actually trained the model called Betatron GPT. It's a GPT-3 it's a GPT-3 architecture. If you look at ChatGPT, it's GPT 3.5 with minor tweaks over the GPT-3. We trained two models. One is the 5 billion parameters, and the second is the 20 billion parameters. It sounded are there public data sets available to train the model? Yes. So if you look at the NLP literature, there's the PILE data set, which that's public from the general domain. If you talk about clinical domain, no, very little. Mimic is probably the only publicly available data source that have EHR nodes that's publicly available. That's kind of the barrier for us to train these large clinical language models. NYU had a paper out last year from they trained a model with NYU Health, but that's much smaller. I think the limitation is these proprietary clinical data. To some degree, is patient privacy issues. Even tokenized data still have privacy issues to some degree. I have tons of discussion with my legal on that in the past few years. We actually have a license on GPT models, and then and we actually made it available. If you want to use the Gatortron and Gatortron GPT, it's accessible. Gatortron, the BERT model, is fully public. You can get it from the Hugging Face. You can download the Gatortron model. You can just play with it, and this is where all other studies have done using the public Gatortron model. These are not my studies and our team studies. And as you can see, some of the studies are very recent, even September last year. And Gatortron surpassed in terms of performance on clinical tests. It's still state of the art. This is actually old. GPT-3 back in 2020 when it came out, people are doubtful on GPT models' behavior, and this is just one of the examples. They come up those hallucinations and biased outcomes that make no sense. So this is the MIT Technology Review. At the time, people were saying to understand why is because these statistic probabilities to spitting out these data, it doesn't really have the human thinking. And nowadays, there are new techniques coming out from AI, for example, chain of thought, reasoning capacities, make it more behaved like a human. So it does make more sense. So this is the Gatortron GPT model, which is a generative model. And the BERT model is not a generative model. The GPT model is a generative model. In this study, we did it's not a true Turing test in Turing test sense, but really present true clinical notes versus Gatortron GPT generated clinical notes to a group of physicians, and then ask them to differentiate in terms of linguistic readability. Obviously, GPT model have no issues, and then whether there's a difference in clinical relevance. So I have to emphasize it's relevance, not clinical significance. Physicians cannot differentiate it, but this is only generating realistic fake content, still fake content. These models by default still do not think or behave like human. So this is one of the example. I don't want to read through. On the left is the real notes, on the right is the generated notes. And as you can see, the generated notes in a lot of places makes no clinical sense whatsoever. So there's still a long way to go from a model to real world use cases of the GPT models. So that's actually our task now, how to leverage these large language models to do some real world applications. And this is a topic we've been collaborating with NVIDIA in the last 6 or 9 months. Clinical trial eligibility criteria screening is not the new novel topic. There are historically a number of work in informatics community already, but obviously these large language models made it seem that it could be useful to automatically ingest the clinical trial information, the eligibility criteria, and then based on the clinical notes of the patient, can automatically determine whether a patient is eligible to a clinical trial or not. There are industry, I don't know about Cornell clinical practice, but at UF we actually implemented some industry systems using to actually screen EHR, including nodes, to identify eligible patients to boost the patient recruitment. So we set to try the Gatatron GPT model to do this. The pipeline is fairly straightforward. The first part is to take in the clinical free text eligibility criteria information and decompose it into what we call clinical traits. So here's an example. On the left, oftentimes the clinical trial eligibility criteria are more poorly written. So we have to tease out the core concept and then constrain on the concept. So on the left, you can see criteria saying patient with uncontrolled hypertension, which will decompose and identify as hypertension is the core concept, and then the constraint is uncontrolled. This is actually public data, so we actually use GPT-4. It actually has the best performance. That says something about the GPT-4 secrets, which we still don't know yet. And then the other part is processing the clinical nodes. We've done tons of different experiments, and then we find the first task is actually identify the relevant blocks of the clinical narratives related to each of the key concepts. Otherwise, you're going to have too much noise into the pipeline. It's impossible it's just too noisy to and influence the model, but also practically, if you try to loop everything into the large language model, it's just going to take too much of time to run. So we can pre-processing this based on the core concept and constraint, identify the relevant blocks for that particular concept and constraint in each patient's clinical notes. And we're primarily looking at history and presentations, and depending on the kind of study or disease we look at, pathology reports and radiology reports, obviously. And then the other part is the eligibility determination. So for each patient, for each criteria, we process the selected node blocks, then correspond to each of the criteria as the prompt, and then using Gatatron GPT to determine whether the patient is eligible for that particular criteria based on that particular block. We aggregate them into criteria level. As you can see, one criteria can be decomposed into multiple study traits and core concept through chain of thought to determine eligibility for this patient for each individual criteria. And then aggregate through another chain of thought activity through the Gatatron GPT to determine the patient level eligibility. We did it on two cohort. One is the ADRD cohort, which we manually annotated by 5 annotators. And on the individual clinical note block level, we mark it as eligible, not eligible, or we cannot determine to train the initial models. And then the other cohort is a cancer cohort where we actually have 2 gold standards. So, most cancer centers are using ENCORE for clinical trial management, where they track the patient that's screened and consented. So that gives us the natural gold standards. We don't have to manually curate these training data. Oftentimes, is the barrier for these AI algorithms. This is the summary. We tried a different cohort. We trained it. We tried different combination of experiments. We trained a model using ADRD cohort and then tested on the cancer cohort. We trained it on both and then tested on each one of them. As you can see, the performance reasonable. Again, it's still a smaller sample size. We only have a couple thousand patients and 10, 11 different clinical trials we are evaluating. But the conclusion is these large language models can determine eligibility just purely based on clinical notes and free text criteria. And the large language model can actually learn from different cohorts, even though they are very different. But the knowledge are very hard to actually transfer from one cohort to the other, as you can see from the performance. And the other experiments that we are currently working on actually is combining the structured data. Right? So the structured data is still meaningful in eligibility criteria determinations. In the last few slides, I will talk about 3 studies on a high level. This actually a collaboration with Cornell collaborators. Faye is a good friend, is a good collaborator. He and I actually have several wins together exploring real world data, and he's the true AI expert. So if you are looking for AI talk, go to Faye's seminars, and he will be more engaging than me. I'm more or less an applied person. So this is one of our early drug repurposing ones looking at drug repurposing signal for Alzheimer's disease. And the idea of drug repurposing is fairly straightforward, as most of you know. And as a matter of fact, in the current AD or Alzheimer's disease drug pipelines, almost 40 to 50% of the targets being tested in trials are repurposed drugs, are actually not new or novel new moleculars. So our idea is to leverage the knowledge in existing biological knowledge bases. When you integrate it, you can do GNN graph neural networks to tease out the relationships between drugs to the final target, for example, a gene of related to Alzheimer's disease. And then we want to validate it in a real world cohort. And again, this is still hypothesis generation. It's not hypothesis testing. But a few key issues with real world data is it's noisy. A lot of the data are missing. This is where the NLP comes in. Taking Alzheimer's disease as an example, cognitive tests like MoCA scores, MMSE testing outcomes are only available in clinical notes. So you have to really, for your AI methods to work, you have to have those as discrete variables. So NLP is important. And then computable phenotype is important and help to reduce the misclassification error. So if you have clinicians, you know just the differential diagnosis process, you know the diagnosis code doesn't really mean the patient has that disease. This is where the phenotyping algorithm helps to reduce, not entirely eliminate, misclassification errors so that your study is more robust. And then the other part is about how to design a study. This observational data, you have tons of different biases, how to mitigate biases through rigorous study design. And trial emulation and trial simulation is one of those. And the underlying methods are not that novel. Maybe it existed in biostat and epidemiology for years for causal inference on observational data. Even in computer science, if you read Pearl's Turing Award paper, it's all about causal inference on observational data to some degree. So the methods exist, and we really just put a AI and machine learning spin on that, following the rigorous study design to do the evidence generation, hypothesis generation, sorry. This is another study that we have in collaboration with University of Pennsylvania about rare diseases. The study itself is nothing fancy from an AI world, because at the end, we're really just creating prediction models to detect rare diseases. And I'm not a clinician, so I'm not even gonna try to announce these diseases, but these are all rare multi-system diseases. And Peter Merkel is a world-renowned rheumatologist at UPenn, specialized in these rare diseases. And the clinical issue is how do we identify them early on? For example, in primary care setting, some of the signs and signal, can we detect them through prediction models? so that we can refer them to rheumatologists or specialized rheumatologists to order the right clinical test to do the diagnostic models. Why it's important in my talk is, again, computer phenotype to define the real outcomes is very critical. These rare diseases will be even harder to find in your EHR dataset because they appear very rarely. Misdiagnosis is often happen. So if you really just use diagnose code to identify the outcome as the prediction task, you're going to have a huge bias in your prediction model. So our main focus in the last 2 years, it's only a 4-year grant, but in the last 2 years, we're developing methods and doing these chart reviews to efficiently develop computer phenotypes to define these real outcomes. This is another study that Faye and I have is really just show that there are other opportunities for real world data. For example, using real world data to help with eligibility criteria design. This is actually recommended by FDA. FDA actually have specific guidelines about using real world data, looking at enrichment strategies to identify specific population that's suitable for specific trials. And using real world data and testing these different eligibility criteria in silico helps us to actually design the eligibility criteria before we run a trial, so make it more confident. But again, as you can see from the overall framework, we pay very close attention to computer phenotypes, missing data, causal inference, and federated learning. And I only have a few slides, so I think I'm good on time. The common theme across these real-world data projects that I picked out are computer phenotypes, natural language processing, social determinants to some degree, causal inference methods on observational data, linking these different data sources to create a more complete picture of the patient. And real-world data have real-world problems. I already talked about that quite a bit. Misclassification is one computer phenotype can help mitigate, but you're still going to have misclassification errors. Just take Alzheimer's disease as an example. From the way how we develop computer phenotype through comparing it to chart review, but that's still a civil standard. So that's not actual, right? Because Alzheimer cannot really be diagnosed. The biological definition of Alzheimer is autopsy of the brain at the end. So it's not a true gold standard. It's a civil standard, right? So there's still misclassification you have to account for in your study design. But being able to actually accurately measure it can be introduced into a bias term into your analysis pipeline. And then the second part is the missing information. NLP is critical, already talked about it. And then obviously there's a long list of other data types that are not readily accessible for research that's generated through routine care, imaging, genomics, microbiome. As CIO for your health, we have key initiatives on all of these data domains, trying to make them available for research. A better data infrastructure, obviously, from my perspective, is very important. And obviously, selfishly, it's my job security to some degree. And also, these are important. These real-world data and study design issues are important if you look at FDA's three-part approach to evaluate applications of real-world evidence. Whether the data are fit for use for the purpose of the study, whether the trial or study design are used to generate this evidence are adequate, and then whether the study conduct meets the regulatory requirements. So the first two really speaks to data issue and then the study design and analytic issue. So assessing fairness for real-world data is critical. This is actually coming out of FDA guidelines, and they talk about specifically about data reliability, how accurate data are, the data assurance. If you have interest, you can read all those. And they all have ways to address, obviously. And then data relevance. It talks about whether the analytic tools are sufficient to actually generate adequately answer the questions. This is not meant to be read. These are just some of the FDA guidance about consideration for state design data using real-world data. So if you have interest in this area, could be a good reference to take a look. I want to jump to the last point I want to make is everything I said are retrospective studies. We talk about predictions. Prediction and intervention are very different. And even from a modeling perspective, prediction models, associations, intervention modeling, you need causality before you can do interventions. So AI must consider causality for intervention model. There's plenty of methods already out there in causal inference in both the traditional biostat and the epi literature, and as well as in machine learning and AI literature. And there are tons of new methods coming out. Being able to vet them, choose them, use them is critical when you're looking at interventions. Data and research infrastructure are key. There's also the need to transition from modeling and infrastructure to real impact. So this is the last study I'm going to highlight. This is actually one of the new ones that we have. It's the official notice of award is not there yet, but it's 2 percentile, so I assume it's going to get funded. So regardless of pay line. But idea is 3 aims looking at social risks in dementia care. This has everything we talk about so far: computable phenotypes, NLP, social determinants of health, about real-world data to build these cohort to create models. One is what we call polysocial risk score, using this large data to predict whether a patient has high social risk or not. And we're using it as a screening tool, not as an intervention tool. And the other aspects of these prediction models are fairness and disparity. Obviously, when we talk about social determinants, we have to be aware of disparity and fairness. So we introduce fairness methods in the modeling piece. And then the second piece is the causal effect estimates of what we call actionable social determinants on the particular outcomes. And the aim 3 is to build a clinical decision support tool so that we can accurately identify patients of high risk, high social risk, not clinical risk, but social risk. And then based on the causal estimates, identify what are the most actionable social determinants that would have the best return on investment if we intervene on them, and then link them to the social services. So at UF Health, we have something called Find Help implemented in Epic. So we are leveraging that tool to find community resources. So it's what I think as a learning health community, collaborating with community partners, and how to actually deliver these interventions guided by AI models. And the last piece is, I don't know about Cornell's situation, maybe Tom would know better. A lot of the issue we have is the infrastructure. We don't have a great testing playground for these AI models, and it's oftentimes difficult. So at UF Health, what I've done as part of the CIO initiative, one is data, obviously, make the data available through OMOP on Fire to support clinical decision support and to support other downstream application development, but also creating the true Epic sandbox. We actually created our Epic sandbox It's a true mimic of the production Epic system, gets updated every week. It's real patient, it's real system, and it's the playground for vetted investigators. Obviously, we have to protect patient privacy to test their AI applications in real world. So I think I'm going to end there. Yes, great.
That was terrific. We really appreciate you joining us today. Any questions for Dr. Bian? I'll ask one question, a little detail oriented. It was really great learning more about Gatortron, an early application of GPUs to clinical techs, and not just an early application, but an effective one. On one of the slides, you described that Gatortron was superior for certain tasks, but not one particular task as compared to data out of Encore. I missed all of the details there. Could you please clarify?
Yeah, so that's a fluctuation that we don't know. We're digging into it right now because the sample size is really small. So I'm not sure if it's a true error or it's something about the training data we have. And the Encore data obviously only have the final gold standard. It didn't have the intermediate annotated blocks because we didn't annotate it. So that may be the missing piece causing the issue. I have a question about Sandbox. First, you have to be willing to move to UF Health. It's UF Health patient. It's UF Health Sandbox. But publicly, Epic does have Sandbox. The problem with public Sandbox is it doesn't have real patient, and it's not real clinical workflow that you can test. So I think working with Tom and your Weill Cornell health system lead and figuring out where's the potential to get access to them and be a partner with them. I think that's the other issue with working with a health system. You have to be partner with the health system to do a lot of these development and implementation.
Absolutely. I'm happy to field questions from folks afterwards. We are drawing to the top of the hour, just about out of time here, but thank you very much, Dr. Bian. We really appreciate you being here. This was an outstanding contribution to the seminar series, really helping Weill Cornell CTSA folks get a much better sense for the state of the art in artificial intelligence and real world data. Thank you very much. Thank you all for joining, and we'll see you soon. Take care.
All right, thanks. Have a good one. Thank you all.
Thank you.